So IntelliSuite software as such has various modules. When there is an installation of the software, we have various modules that come on the desktop. So this is a folder in the desktop and which has various modules. So now we shall look at how do we create a simple cantilever design and try to simulate it. Okay. So let me show you how we can um, create the design and what do we want to create is what we will see first. Okay. So let me take the help of Paint. I would take this as my whiteboard. Okay. So a simple cantilever beam, the top view. So here, this is the top view. So please understand that there is one more cantilever beam below that. So now this is a side view. So on the left, what we see is the top view, and on the right is what we see the side view. So this is what we are trying to design. So now what do we do with this design? So what do we understand from this design is it's a two-plated cantilever beam. When two-plated cantilever beams are present, we can learn how to perform a electrostatic based simulation. We can learn to perform a pressure transducer based simulation based on the physics, and it can be a thermal electrical, it can be thermal mechanical, it can be electrical mechanical. So various various sensors for various applications can be derived from a two-plated cantilever beams. Okay, so let's start with the basic one. So here, to start with, we have the module called 3D Builder. Okay, so here, let me also give you an indication that I'm starting the module, the design using the 3D Builder, but I wouldn't recommend it for any beginners. And I'll also tell you where we could hit a problem or it consumes a lot of time to do it, and what is the shortcuts to adopt this tool effectively is what we will learn. However, since I want to show you how the design may look like, I'm using this module for now. So I just drew a 2D layout. On my left panel, a 3D structure is created. So this is a random way of designing it. So instead, what I would do is to take the tools, take the shape, select the shape, tools, keyboard. So here, this point is the origin point, and let me try to write the coordinates here. So this shows us that the coordinate on the x and y is negative and diagonally opposite coordinates are positive. So now we have two coordinates, two system coordinate which are diagonally opposite to each other, and this creates a rectangle of the length 300 micrometers. and the width of 100 micrometers. And this is level 0 by default. And now I want to create one more beam of the same size, but I need to create a gap between the two. Hence,
Siripat, I have a
yes,
question here. Sorry. You are saying
yeah,
that on the right side, it's a 3D model.
yes,
So we have not given it a thickness or the Z
correct.
dimension. Yeah.
That's right.
So how we can, is it a
Yes.
default value that it's taking to make
By
it like
default,
3D?
it is 1 micrometer thickness. You can always modify this by entering the height of that value.
Okay.
So now the thickness is changed. So now level 1 is of 10 micrometer. So I can
Okay.
select that level, and right side you can see the button called modify height, and then I enter 20, so it increases the thickness. Okay. So now I go to level 2 and then apply, sorry. So I select the same geometry, and then I enter the same value, minus 150, minus 50, 150, and 50. So now I have created this geometry. I still modify its height to 10 micrometers. The gap between the two is 1 micrometer. Instead, I will say 5 micrometers. So this becomes easy for me to define its height. So the thickness is all relative. So I'll just reduce this to have a better clarity. So the bottom beam is 5 micrometer in thickness. The gap is 5 micrometer in gap. The top beam is also 5 micrometers. This is a simple structure that I can draw it. Okay. So now I hinted saying that I wouldn't recommend to use the 3D Builder module to start the geometry directly. The reason why I told you is we are creating structures which have to be compatible with FEM, finite element methods. So now in the case that you are seeing, the two beams are not connected, or two beams are not touching each other. Assume that I have a rectangle in between the two. Now I have a problem because it is not giving me a compatible mesh. See, I can see two misalignments found. So, as a beginner, when you start working on 3D Builder directly, and if the geometries are connected one above the other with various materials, then we may have to do a lot of juggling around to mesh the design. So we need to auto remesh. So we have to abide to the rules of FEM. So instead, what we recommend is in such scenarios, in such scenarios, we always recommend to use the module called Blueprint. A blueprint is a layout editor which creates a 2D geometry, and the same 2D geometry can be imported on the 3D Builder module and define its thickness. So this will take care of my FEM issues. So currently, let me come back to similar case the later stage. Let me move with the existing design that I've already made. Okay. So I hope it's clear the content that I'm trying to show you is giving you clarity. In case if you have any questions, you can always drop it on the chat box. Uh, I can try answering them. Okay. Okay. So now, what do I do with this geometry now? So now this geometry has a two beam structure which has a similar color. So now, how does that matter to me? I need to change its color because for following reasons. The top beam can be a metal, the bottom beam can be a silicon, and vice versa. So the software identifies different structures uh, uh, with different entity. We call it as entity only. Okay, let me put it this way. So you can define unique material properties, unique boundary conditions, and unique load conditions only when there is a change in entity, basically color of the geometry. So now, if I have to do an electrostatic based simulation, then if the two beams are of the same entity, then I have a problem because I cannot give a zero potential to one and a positive potential to another because both entities are same. Okay. Instead, if the two entities are different, then the software differentiates that it's two different entities and I can define two different voltage conditions. Okay. Same goes with the material properties as well. Common entities are with same material properties. So now please remember that I'm trying to save the file which I've created at just a geometry. It's no link with material properties or any loads, boundaries, nothing. I have just created a geometry as it is. Let me create, see.
I have a question, Dr. Shripad. When you say two
Yes,
entities, like they can be different materials because, like, in case of a capacitor, let's say, like the two beams can be silicon, right?
yes,
It can be,
yeah,
it doesn't have to be
it can
different
be.
materials. Okay.
It can be. Yes. So I have saved this file and let me push this off. I need to check the mesh conformity and connectivity and then click check. And then the software doesn't know what type of simulation you're trying to do. So we, based on what are we trying to do, we do the thermal electromechanical and then click OK. And it will hint me to save the file. So it's has no condition here to give any file name, preferably avoid alphanumeric uh, or only numeric as a file name because software may pop up some errors during the simulation. And preferably avoid a space character when defining the file name. Okay, so now we have pushed this design to a module called thermoelectromechanical where we can do multiphysics based simulation. Okay. Okay. So now we are good to go to perform simulation. So now this is a UI which allows you to set various simulation settings. So typically in any of the software, you need to search the menu options in a sequence. So here, it's in the sequence here. Simulation, define material properties, define load conditions, boundary, mesh, perform your analysis. Okay, so now let me go to simulation and simulation settings. In simulation settings, what do we see? The calculation type. What do you want to do now? You want to perform a static simulation or a frequency or a dynamic based on your preference. Another preference is what is the physics behind it. So you want to perform a stress displacement where something like an example, like I apply a pressure and see the deformation, that's stress displacement. It could be piezo resistive or a piezoelectric based simulation where it is a stress dependent. Heat transfer is with some heat convection, how the heat dissipation happens across the geometry is what we see the heat transfer simulation. The heat transfer thermal stress is due to heat. Is there any stress or deformation that happens? And vice versa. If it's a stress uh, based input, which is again a mechanical load or electrostatic, sorry, the mechanical load like the pressure. And so was there any heat generation or the change in temperature around the device? And thermal electrical is like a thermistor or a thermal a gas sensor where you try to make it more sensitive by heating them. So it's more of a thermal electrical simulation. So basically what I'm trying to tell you is based on your physics of the problem, you choose the analysis type. Okay, so we're good to go now. So now let me select thermoelectromechanical relaxation, and this will allow me to perform electrostatic based simulation, and due to the electrostatic force there would be a deformation. Okay, so this is where I'm trying to set. So now I click, I apply, okay. So let me go back to my drawing. So now what do we see as an output is a deformation. Probably I'll take this of the top beam like this. There would be a deformation of the top beam due to the electrostatic force. So now I select, click, check, modify, select the geometry. I would say this to be a bottom layer and double click, and then I select top layer. I'm showing you this with nomenclature saying that if there are multiple materials, then you can give the material name itself. So just for our understanding, I just stop. So bottom layer, the one which is turned red, import. I can select any material that I wish to. So if by default, everything is considered polysilicon unless we want to define something different. So let me take a silicon 100, and these are all the material properties that we have with Si100. So now I go back and verify one by one that how about the material properties? The material properties as such, if I want to change this, then I can always change it. In some literature, we have a 0.22 as the Poisson's ratio, and some may not have it. So based on the material properties that you want to change, you can always change it. Okay. So this is the bottom layer. And it's done. So now I have the top layer. So import, and I would say that this would be a metal because I want to see a deformation, but for which there should not be any stress driven. So naturally, I would select a material which has a better Young's modulus and high conductivity because we are performing electrostatic deformation based simulation. So similarly, we define stress gradient. So you can always check how do you want to define the stress gradient. Thermal electric expansion of coefficient based on the type of material that you use or choose. We can always define the material properties. Thermal conductivity, specific heat, dielectric. If we are performing a crystalline oriented structures based materials like quartz, lithium niobate, um, piezoelectric materials which have dielectric constants. So you can always define the dielectric matrix based on the type of material, orthotropic, anisotropic, variable isotropic, variable orthotropic. So it's something like what you see, the D11 is its position here. So if I want to change D11, then I would go to this position and then type my values. So D22, this is my position, 23E minus 7. So I can always define the material properties this way. Okay, so you can always check whether the material properties really meet your requirement. With regards to piezoresistive, I'll come back to this a little later with an example. So I have defined the top material to be the gold and the bottom material to be silicon. So we're
Dr.
done with
Raja,
simulation. Yes,
there is a question in the chat. Stress gradient, can it be a vector?
yes, you can get that. So now simulation setting, materials are done, loads. What is the type of load? We are trying to simulate something which due to the deformation due to electrostatic force. So I apply 30 volts to this and a 0 volts to this. So now boundary fixed. So I need to fix a boundary condition. I would say select the bottommost and don't try to click on the geometry to rotate the structure because the face will get selected, so which could be misleading for you. So use the outside area, hold the left button of the mouse and try to rotate the mouse. The geometry gets rotated. I select. Okay. So now we are done with boundary condition. We are going to mesh. So now mesh is a tricky thing because high refinement in mesh always give better accuracy, but we have to compromise on simulation time. So now what I would say is this is a 300 micrometer by 100 micrometer geometry. Mesh it to 30 micrometers. Now, the bottom layer is a fixed geometry. It does not participate in any of the physical movement of the device. It's die attached. So why do you want to create elements on such geometries which are fixed, which are not allowed to move? So this will help in reducing the number of elements for the computation for better analysis or faster analysis, to be more precise. So now I would suggest go to mechanical mesh, modify, pick on geometry, and then I would say only this geometry. I want to reduce the element size to 10 micrometers. Then I go to update mechanical mesh and then click update mechanical mesh. Only the one which has the deformation capacity is meshed effectively. Okay, so this will help. Now, we all please remember that we are trying to do an electrostatic force-based simulation where due to the electrostatic force, there is a deformation in the geometry. So whenever we are applying electrostatic force, it is recommended to use a modify electrical mesh. So I click on geometry. I would say that this has to be split by 2, and then each element will be split by 2, and then we update the electrical mesh. So now the electrical mesh is applied, and the first element that we applied is the mechanical mesh, that is called the FEM, finite element method. The second one that we applied is the electrical mesh called the boundary element method. So we have combined FEM plus BEM in electromechanical based simulation, and then I run my analysis. And this is an iterative process, and by default it has to run 10 iterations. However, I have set the accuracy to 0.001. So simulation may terminate if the iteration repeats the same value. So simulation is done. Let me see the results. I would say based on the maximum deformation, it would be in Z direction. Okay, so this is how we see the result. And we see the deformation. So here you can set the accuracy for the simulation. And here we see, since this is a capacitance stuff, you can see the capacitance between the two due to the displacement. So the displacement, the maximum is the negative shows the direction. That's it. And this is how you are seeing the simulation results. So I'm not really concerned right now that whether the simulation output is correct, not correct. I'm really not concerned. I'm just teaching you how to use the software. So we will get into device specific cases when you start using the software. Okay. So now I can use the same to perform.
We have another question, Dr.
Yes.
Raja.
Yes.
So for the boundary element method, we do we not need to apply to both top and bottom plates?
Well, for boundary element method, when you apply the boundary element mesh, it identifies those entity which have potential defined. So it picks up automatically based on that material. So in this case, as also in this case, let me show you. Go back. So even in this case, we applied boundary element method only to the top beam, but it has also considered for the bottom one because it is defined as potential zero.
And forgive me, but like why do we see like non-uniform deformation here in the center of the beam in the
Non-uniform
result?
deformation. Yes,
Yeah,
probably I'll
because
have to. Yes, so I'll have to just refresh this, I guess. Let me go back, check this. Yeah, it's all good. Let me check this. Let me save this again. Mm, we have applied. Sorry. Yes. Let me refresh this. Mesh. Update electrical mesh. Yep. I think it must be good this time. Let me run it again. I think there was some issue with the mesh, I guess. Let me check this again. Yep. I think now it's fine. Yeah. So here, what you see is the maximum displacement,
yeah,
4.36 nanometers. The scale is in micrometers. So the maximum displacement is 4.3, the force that is applied. So now I can check the 1 minus stress. So this is my stress profile. I can push this. Okay, let me also show you that it's a linear motion. The displacement is in nanometers, so I need to increase the scale for me to show you some animation. So you can see that there's this deformation that you can observe. However, this was something which we had much earlier, and now we have something called as visual ease. So we can do a post process for visual ease. We click this. It generates a post-processing file, post-processing simulation files, and then we can open in Visualize and select the file to have a better, oops, sorry. Uh, Open Visualize, select 10th one, not found. Oh, tech plot file missing. Okay, I think there's some issue. Let me So, okay, so let me show you here. I think we'll see what's the issue there. Why post-processing file are not being generated. Okay, so this is how we see the deformation. So the stress, the mice stress, the stress profile, and directional stress, and SP1, SP2, and SP3, and the change in capacitance. Okay, so this is what we get. Now, the one common simulation that we see with electrostatic or electromechanical based simulation is a pull-in voltage extraction. Okay, so pull-in voltage extraction, apply. Instead of applying a fixed voltage, I would say that I need to apply, probably I'll delete this and then freshly apply voltage entity on the top, 50 volts, sorry, not here, input value range, 50 volts, sorry, 0 to 50 volts in the increment of 10. I'm just choosing 10 because of the interest in time. So now it performs a simulation from 0 volts, checks the deformation, 10 volts, checks the deformation, 20 volts, checks the deformation, and up to 50 volts, the simulation keeps running in the iterative mode. So click OK. Oops. So I would put 50 and 10 and then remove this. So I have, sorry, 0, 50, increment of 10. Do I see that? Yes. Okay. So now I have this. Rest, everything else is the same. I've just changed the loading condition and then I can run, oh sorry, I need to apply electrical mesh. So now the same simulation runs for 6 times because it has to run for 0, 10 volts, 20 volts, 30 volts, 40 volts, and 50 volts.
We
So
have a
the,
question in
yes,
the chat, Dr.
yes,
Raja.
yes.
So Elmore asks, like, will we be able to see the deformation on the analyzed geometry that has color code instead of the one with the mesh that you showed?
You want to see the number, I mean the deformation, the magnitude?
I think so.
Can you, because since I cannot see the chat box, yeah, so whoever has asked me the question, can you tell me?
Deformed shape. Uh,
Yeah. Oh, yeah. So you want to see the deformed shape? Yes, there is a
yeah.
deformed shape I can show you, where you can always use it to take images, or save it as an image file. So here I would also hint at typically electrostatic simulation or electrostatic force-based mechanical simulations are generally recommended to perform a hysteresis-based simulation because of the metal-metal contact, the stiction issue, or it can be deformation due to the electrostatic force. So for those people who are sensitive about such work, then I would suggest to use the same methodology to use this simulation for hysteresis analysis. Like the way we have set the voltage, I think the simulation is complete. Let me go back to that. So here we have up. We have selected up. Up meaning 0 to 50 in the increment of 10. Bottom is 50 to 0 in the decrement of 10. If it is both, then 0 to 50, 50 back to 0. That's the hysteresis plot. So you can always get the hysteresis plot. So now let me see the plot. The x coordinate is voltage, the y coordinate is z displacement. So I have a pull-in plot for which I can get the data. I have 6 data numbers, and this is what the deformation looks like. So you can just play with this graph. So if you want to take this to an Excel file, then you can always do it by copying this and pasting it to Excel. So you can always play with this graph by defining the area, the points. Um, so these are the points which I marked it crossed. So now this is the pull-in plot. I would say a displacement versus voltage, or the voltage versus displacement. So now if I set the increment to 2, then 0 to 50 in the increment of 2. So the simulation may take longer, but we have more data points here. So similarly, we can extract the capacitance. So now between the two. So this is the capacitance for the change in voltage due to the displacement. So now with the two graphs, I can derive the change in capacitance due to the change in displacement. And this is all the maximum value. Let me be clear. So it's all the maximum value here, what you see.
So typically, like the model does not converge when we are very close to the pull-in voltage. So we'll be able to extract all the data from before those voltages, right?
That's a good question, Suraj. I was about to come there. Now, there's something called as contact analysis. I wouldn't check this during the training because it would take a little more time. So what is this contact analysis? Contact analysis is something where you define a specific geometry as face A, face, F-A-C-E, face A, and the another geometry as face B. So let me show you that. So I go to contact and then face pair and then in face pair, face A. So this bottom is my face A, and the sorry, I think I'm using my laptop which is consuming a lot of memory. So here I select contact analysis, uh, then face pair, face A. The bottom one is the face A, which is deformable. and this is face B, and I would say it is rigid. So when I define this, then assume that I'm applying the voltage 0 to 100 and the pull-in point or the touching snap-down point is at 70 volts. Then when the geometry gets to know that it has touched the bottom and it cannot go beyond that, the simulation converges there and the results are produced.
And I guess my follow-up question would be like, for example, in a comb drive arrangement, like will we be able to choose multiple faces as face A?
Yes,
Okay.
yes, you can do that.
So
Yeah.
so would you be able to show the deformed shape that Almore requested?
Yes. I think let me run the simulation again. Just got crashed. Just give me 2 minutes. Oh, okay. I've checked this box, so it will take large displacement. So I just no, let me not check this for now. It may take a long time.
There is another question that has two more
Yes.
questions that have come
Mhm.
up. So one is from Alame Mehdi. Would you please also show the fringing field effect? Is it required to define the gap spacing area with a specific material?
Okay. Yeah. Okay. Fine. So the deformed shape, uh, input scale factor, I would increase because the deformed scale is too small.
Yeah.
So this is the deformed scale. If it's more required, it's always recommended to have a better deform scale. So you can always take this. And for better accuracy, oh, I think for this mesh is required. Yeah, so else you can always take this Z displacement and let me see if I can get the force process for multiple values. Let me see. No, I think for multiple values, I don't get it. Okay, so yeah. So here you can linear motion. So this you can see the displacement.
And regarding the question about the, would you please also show the fringing field effect? And is it required to define the gap spacing area with a specific material?
Well,
Like, I think it's about the dielectric that goes between the two plates.
yes, yes.
Yeah.
So
Yeah,
it's
like a
all
air.
about the geometry that you want to add in between the two and then define its dielectric property, and that's it.
So by
So,
default, does it take air as a dielectric
Yes,
material? Okay.
so one has to
yes.
make the same box and define air as a dielectric.
No, he did not draw any box in this
No,
case.
but yeah, regarding that question, so if someone has to define, so he has to make the box with same dimension and defined as a material property as an air dielectric.
Stop animation. Okay. So now let's see.
So,
Yeah, sorry. Yeah.
yeah, so as Kadir was asking, so like, for example, instead of air, if someone has to define the dielectric as some kind of a polymer or something else, so they need to draw it as a structure in between the
Yes,
two
you have to
electrodes.
draw that as a structure in between
Okay.
and
But yeah,
define its properties.
but for the air, it is not required. It is by default.
Yes, that's right.
Okay. And then there's a question from Almore, like for the contact simulation, will we also get the contact area and force? And when we have overdrive, will we know
Yes,
how far we have gone beyond the contact?
yes, yes. If you want to know how far you have gone beyond the contact, then don't check this box called contact analysis. If
Okay.
you, yeah, if you want to know where it snaps down, so then check the contact analysis.
Okay. Yeah. Thank you. Before we start, like just a follow up on the last question
Oh,
about the
yeah, okay.
dielectric material in the spacing. So Mehdi is asking, like, if for air we do not need to define the structure, then how can we show the fringing field effect?
No, 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 no. Other than the air that you want to define as a dielectric material, then you have to draw a geometry and define its properties, dielectric properties, and the material properties related to that.
Uh, yeah, I think I understand that. But like, I think his question is pointing more towards like for in case of using air as a dielectric. You had mentioned that we do not need to define the structure because it assumes by default that there is air
Ah,
between the
okay,
conductor.
okay. So
So
during the simulation, the
yeah.
dielectric that is considered is one.
Mhm. So,
Yeah.
like, can you show like if there is a way to show the fringing field effect in the dielectric layer? Like, for example, in the model that you showed just now.
Ah, okay, okay. So in the
Yeah.
model that I've showed just now, I cannot show it right now because
Okay.
getting a fringing field is not straightforward in the simulation. Okay, so it's a little tricky. It's not upfront like because it gives a planar capacitance, but getting a fringing field is a little tricky.
But it can be done using the tool.
It can be done, but it would take some more exercises that we have to go through it.
Do you have
Okay.
any
Yeah.
example ready?
No, related to
No.
fringing field, I don't have it. Probably,
In
I
any
think I
of
can
your
create
video
one.
tutorial? Okay.
Yeah, I can create one and then probably showcase that in tomorrow's session.
Okay. Yeah, that would be good also.
Yeah. Okay. I've stopped sharing my screen. I didn't realize this. Okay. Okay. Okay, can you see my screen now?
Yes, we can.
Okay, great. Okay. So let me move on to another. Okay, so like the way we had thermo-electromechanical relaxation, we can perform stress displacement, heat transfer thermal stress based on the physics. So either you want to see by giving one specific input and want to measure another specific output. So it can be thermal, electrical, mechanical. So now here I have, let me apply pressure of say 1 E minus 3, 1 kilopascal of pressure. And then I clean up the previous analysis. And then, oh, sorry, I think I have to select static analysis. Analysis, start static analysis. So yeah, so this is due to the pressure that we have applied, the deformation is seen. So same goes with a capacitive type of a pressure sensor, whether it's circular, planar circular, planar rectangular. So the simulation setting goes as it is. So in the case of capacitive pressure sensor, what we would do is select thermo-electromechanical relaxation, and then we apply pressure, also apply voltage. It's a little tricky simulation because we need to apply voltage which should not be in the range of pull-in voltage at all, because the software, the device have to snap down or to pull down only and only due to the applied pressure and not due to electrostatic force. So electrostatic force becomes very sensitive parameter to for in the case of a capacitive type of MEMS pressure sensor. Okay. Yeah. So this is with the static type of simulation. Let me move to frequency analysis, where we try to find out natural frequency of the device. Apply. Okay. So when we are trying to apply natural frequency, when we are trying to identify natural frequency, we do not give any input load. So I would just clean up my previous analysis and then just run frequency analysis. So the three modes of frequency are here: 305, 491 Hertz, that is 305 kilohertz, 633 kilohertz, and 840 kilohertz of mode 1, 2, and 3. Why did I get three modes of vibration? Because I have selected three modes of vibration here. If I select 6, then I would still get 6. So frequency analysis provides the following information. It, it identifies the natural frequency of the device for with various modes of vibration. So you can check, it has given 6 numbers now. Okay, so what are these numbers? So let me see if I can show you with post-process simulation. Yes, this time. Okay, so mode 1 is this. I just loop the simulation, loop the animation. So this I've just increased the scale, and this is mode 1 of vibration. Mode 2 of vibration. Mode 3. Mode 4. Okay, so this is how we can identify the natural frequency of the device in various modes of vibration. Save this. Now, when I select frequency, then I have the option of the analysis type. It's not just static stress. Static stress is selected to identify natural frequency through the simulation. But if there is change in natural frequency due to heat transfer thermal stress, due to electrostatic force, due to magnetostriction property of the material, then we select based on that physics. So typically thermo-electromechanical relaxation or electrical thermal stress is generally selected when there is impactful, when we want to see that the natural frequency would change due to the applied load. Okay, so in the case of thermoelectromechanical relaxation, we would still get voltage versus frequency graph, because as the voltage increases, there is a negative spring effect that comes into picture. We call the spring softening, and due to which the natural frequency keeps coming down. And such plots can be extracted. Okay, let me see if I can get that. We need to apply voltage for that. 0 to 50. Increment of 10. So it checks the natural frequency at every voltage point and then performs the simulation. So meanwhile, any questions while the simulation is running?
In the chat so far.
Yeah.
Your screen sharing stopped, Dr. Rajan.
Screen sharing stopped?
Yeah.
Oh, okay. Oh, okay. There's something wrong then.
I have a question related to the simulation time. In your experience, how do you find for a similar structure like how would the simulation time be in for IntelliSuite software in comparison to other prominent software like Console or Coventer?
Speed, in terms of speed, it is much better. I cannot quantify it because it all depends on the computation power of the PC, and it also depends on the size of the elements that is created during the mesh.
Okay.
Suraj, I think you need to make me a presenter again because all my menu options are disabled now.
Uh,
I cannot unmute.
yeah,
Yeah,
I
yeah.
don't
Now I got it. Yes.
I don't know why it changed on its own.
Okay.
Sorry about that.
Yeah, that's fine.
Yeah, we can see your screen now.
Yes. Okay, great.
And what are the different kinds of meshes that are possible through the tool?
Yeah. So one is the abacus that we use is a 20 node brick element for
Hmm.
anyone's interest. Okay. So we use 20 node brick element. Other than that, we have uh, tetrahedral, triangular, and cubic or rectangular based elements. We have
Okay.
triangular specifically because sometimes the MEMS device may have curved features where a rectangular mesh wouldn't be supporting well.
Yeah, and it automatically modifies the mesh in narrower regions or things like that.
Exactly. Yes.
So, and you can also choose what particular, for example, in a comb drive, you just around the comb drive fingers, you refine the mesh, and the
Yes.
rest of the structure can be much wider and broader mesh for easy computation.
Yes.
Okay.
That's right.
Yeah, thank you.
So for everyone's understanding, so I'm going a little slow on the training because it also, I mean, you also get the recording later, but in case you if you have any issue using the tool later stage, you can always reach out to Suraj or Khader or anyone at CMC. We are planning to set a channel for to respond to your queries. Um, yeah, at the earliest. Okay, so let me go back. Uh, Voltage, x coordinate, metric frequency. So 1, 2, and 3. So since the voltage is not so significant, there's not much of change in the natural frequency because the deformation is not too long, too large to have a pull-in point. So here you can see that the natural frequency plots are a straight line. So in case if I increase this to a value of say 200, then it would slowly drift and we would get a plot uh, something like this. Okay, so where the natural frequency comes down drastically as it touches the pull-in point. So this is the modes of vibration. And here in this simulation, we extract these details. And in addition to that, you can also extract um, specifically the stress related to a mode of vibration, the stress profile specific to a mode of vibration. Okay, you can also define that. I have a case study on that. Maybe I can share it at some point, a later stage if someone is interested. Okay, and next part of the simulation is what I would like to highlight on dynamic based simulation. So static, frequency, dynamic. So in static, we understand that it's a one input, one output based simulation. Frequency, we find out the natural frequency of the device. And in the case of dynamic, we have two options, whether we want to operate in frequency domain or in the time domain. So here we have direct integration as time domain, the mode based as frequency domain. So the simulation that we did with frequency simulation is also related to dynamic here because here it's a time response. The frequency gives the value. The dynamic analysis gives us the plot. Okay, so here going back again to stress displacement electrostatic. So here we get these options of fixed capacitance option, updated capacitance option, or we want to do a stress displacement, a squeezed film, because here we can also define the medium around the device. So here the device can be in the air, it can be within nitrogen, it can be within some fluid, uh, incompressible, compressible fluid. So we can always define the viscosity and the mean free path of the gas around the device to understand to get the effect of that viscous damping effects into the simulation. Okay, so for that we have a squeezed film damping, a direct integration, and yeah, so and this simulation is available. So here we have stress displacement electrostatic squeezed film. So we define whether if it's electrostatic or it's pure mechanical based simulation. In the case of the last second option of the physics, stress displacement electrostatic squeezed film is specific to electrostatic based device where there is a potential difference that is applied. In the case of stress displacement squeezed film, it's purely a mechanical simulation where we define the material properties, and due to pressure, force, acceleration, loads, the simulation takes the input and corresponding outputs are thrown out. Okay, yeah. So this is the dynamic simulation. I wouldn't run any dynamic simulation during the training session because the minimum simulation time for a better accurate result would easily take somewhere between 1 to 2 hours easily. Okay, a dynamic based simulation. Okay, but I can always point at a few exercises. So let me show you something interesting here. So we have about 20 plus examples of various physics defined simulation case studies. Okay, so here a simple comb drive structure. Let's to start with a simple comb drive structure. How do we perform electrostatic analysis? Mechanical analysis, electromechanical analysis is what we will see. If we have to perform electrostatic analysis, then how do we set the simulation is defined voltage, mesh, boundary, and then seeing results. File open, sorry, results. So here we have multiple of these examples which talk about uh, the electromechanical analysis, the mechanical analysis. So this is a pure electromechanical simulation, and this is a comb drive structure. So natural frequency shift of an accelerometer. So how do we set the simulation? And this is the file. So you can see that it is thermoelectromechanical relaxation. We define the voltage and we see the results. Yeah, so you can see that it's frequency versus voltage. Due to the change in voltage, we have the frequency plot that gets changed. So similarly, we have a lot of examples specific based on the physics. So this is a Joule heating, RF device, electrostatic micromirror, crash sensor, piezoelectric beam, piezoresistive, squeezed film simulations. Okay, so when you really get access to the tool, you can always explore this to a greater extent to learn the software. And all of the files that are shown here are available in the installation directory. So we have DM. So the examples that you see is what we have so many files. Capacitance updated, comb drive, contact analysis, Coriolis force, crash sensor, frequency shift, Joule leading, piezoelectric, piezoresistive. Okay, so I would recommend you to explore the tool to a greater extent with these examples. Okay, so at this point, any questions?
In the chat so far. Please feel free to write your questions in the chat. None so far, Dr. Raja, so you can
Yeah,
continue.
okay. Good to go. Okay, fine. So there are no more questions. So I have given you an overview of how the simulation of a static, frequency, and dynamic are carried out. So I understand that the session that we are going through is just an overview of the software. So I would recommend you to get your hands dirty by accessing the tool to a greater extent provided by CMC now, and it use the examples that are shown with plenty of physics based simulation design files, and probably that will be a starting point for you to learn the tool and to use it to your benefit. Okay, so let me move on to another interesting simulation type called macro model extraction. I will talk more about macro model extraction in my last day of the training, that is day after tomorrow. Okay, so here, just to give a glimpse, is macromodel extraction is a simulation where we can extract many parameters like spring constant, squeezed film damping variables, capacitance versus displacement, rigid body variables. Rigid body variables is something like the planar in geometry details like displacement specific to the node, and the weight of the device, and the density of the device, the volume of the device. So all of these rigid body variables can be extracted with the simulation. Another interesting simulation that we can do is mechanical reduced ordered model simulation. What is reduced mechanical reduced ordered model is ROM, reduced order model simulation, which can help to convert the MEMS device file into a HDL, hardware description language, where we can connect the HDL file from FEM to signal conditioning systems or to circuitry. Okay, so similarly, we can perform electromechanical reduced order model where we see the model contribution, the strain energy associated with each modes of vibration. Once these two things are done, we do the mutual capacitance and complete the simulation part of it. And the benefit of running the reduced ordered model simulation is that we can use the same file of the ROM to perform dynamic analysis. I did mention that a dynamic based simulation is a huge time consuming activity in terms of FEM. In the case of macro model extracted file, it would still be not more than a minute because it gets converted to a lumped model file. The FEM file gets converted to a lumped model file, and we can always extract more information with a shorter duration. I'm just saying it's one minute. So it is absolutely 1 minute or a little over 1.5 minute of simulation where we can get any number of data with respect to time. Okay, so there are quite a good examples related to macro model extraction based on the device that we are working. So I would talk about this macro model simulation in greater detail in day 3 of our session. Okay.
We have a question, Dr. Raja.
Yes.
So Almore asks, for the displacements that you have shown earlier, we have seen maximum values. We could extract values across a certain line.
Yeah, so whatever you saw was actually a last value. the last value, the maximum displacement, the last value. So you can get the journey from what point to what is the last value by plotting the graph. So if you want to see the uh, displacement related, let me see if I can show you that displacement here. Yes. So here you can see the displacement planar geometry data, which you can extract. Just copy this. So this is with respect to the journey that it has made to the last point, X, Y, and Z. And this is with respect to the node numbers. So identify the node number and then you can get that information. Does that answer your question?
I'm waiting for, yes, yes, it does.
Oh, great. Okay, great. Okay. Okay, so Suraj, if everything's fine, should we take a 10-minute break now?
Yes, surely we can do that.
Yeah. Okay, so we'll have
And
a 10. Yes.
yeah, so before we go into the break, I just want to confirm that all of the participants have been added to a MS Team session for the next 2 days of the training as well. So all of the participants must have received another email from CMC. And if anyone does not see that email or see the training in their calendar, they can feel free to drop in the chat and we can look into that. Yeah, please go ahead, Dr. Raja. You were
Yeah.
mentioning something. Yeah.
Yes. So after the break, we will come back and we will see examples specific to piezoelectric based simulations, because that's something interesting that most of the MEMS community is working on. And we'll see how do we set various voltages, various material properties, and why are we doing it. So specific to piezoelectric, we will see that. And we will also see heat, thermal, because what we saw was purely mechanical or electromechanical. So we will also see some thermal based simulation results as well.
Okay, perfect. Yeah, we can do that.
Okay, so welcome back. We saw about the electromechanical simulation and various types. Again, it's frequency-based, time-based simulations. So let me show you one more example that we have here, which is specific to thermal-based simulation. It is thermal stress. So it is more like due to the applied voltage, there is a change in temperature for which there is a deformation that happens. Okay, so it's let's see how the simulation settings goes through. It's a static simulation again. We select thermal, electrical, thermal stress, apply. Okay, again the same story. Material properties. You select, you apply, import material. Also, let me also tell you that in case if there is a material mismatch, like if you want to have your own material which is not available in the database, you can always edit the values, and then export this to a file. So this gets stored. So every time you do not have to change the values of the materials specific to those properties related to thermal, mechanical, and electrical. You don't have to change the properties. Instead, you can save this material property as one file, and then you can always import it back. Okay, so have this in mind when you use the tool. Don't get worried why my material that is required is missing. You can always export it and save it for future use. Okay, and we change the material. So here, let's see what all the loads that are applied. So we have 8 static loads, what we see here. Heat convection, film coefficient 1, sink temperature 25. So here we apply heat convection, that is this portion, what you see in red. So these are defined as materials which are at room temperature. That's why we have 25 degrees that we have applied. Okay, so heat convection. So what is this phase voltage? Phase voltage is these 2 points, what we see here, 1 and 2. These are considered electrodes where we apply a voltage of 0 to one electrode and a voltage of 10 volts to another electrode. And where are these fixed? Sorry, it's to be checked. Check only boundary. So it is fixed in those areas which are turned red. Okay, so now let me run this simulation. It's done. So results. What are the type of results that we can extract? We can extract thermal, electrical, thermal stress. So we have given electrical parameter as an input, heat parameter as an input. So we can extract temperature, thermal, we can extract potential, that is electrical, we can also extract mechanical data. So results, the mechanical data is the displacement. Displacement is dominant in X direction. Let me see if I can push this to post processor. No, I think all static based are restricted, I guess. Okay, so here what you see is the result. The X displacement is dominant. And with linear motion, this is what we see. The displacement is about 2.32 micrometers already, and I have scaled it to 10 times. So naturally, there is more deformation due to the voltage that is applied. So you can extract a potential that was applied. So you can say check that the blue entity is 0, the red entity is 10, rest all is in between.
There is a question,
Yes.
Shirapat. It's from Almer. For
Okay.
the heat convection, as we
Yeah.
set 25 degrees at the fixed area, do we also define temperature at areas that expected to have maximum temperatures?
Yes. Yes. So if you are expecting due to the heat convection or due to the input value, then do not set it. It has to be deterministic by the software. So wherever you feel that those materials are a part of the room temperature, then you can define heat convection to only those phases. Yeah, so does it answer your question?
We've not
Does that
received
answer your
any.
question?
Yeah, we have not received anything in the chat yet, but I think it
Okay,
does. Yeah.
okay, fine, fine. Okay, so this is the Joule heating or thermal mechanical or thermal stressed based simulation. Okay, so you can always define, as I mentioned, it based on the physics, you can always define this. Okay, yeah. So let me go back to one more example, which is quite interesting, is a piezo-resistive based type of a transducer. So at this point, related to whatever we have covered till now, any questions?
Nothing in the chat so far.
Okay, great. Fine. So let me minimize or exit this module.
Okay, there is one question now.
Yes.
So Almer is asking, so the software will understand by itself the maximum temperature caused by the voltage, and it will compare it with the 25 degrees to get the heat gradient of the convection process.
Yes, that's right. That's right. Absolutely. So wherever the geometry gets connected and those in that connecting regions, some regions are based on the voltage that is applied and some regions are based on the temperature around it. So it relates to the base voltage, sorry, base temperature of 25, and then based on that, the resultant temperature in a specific region due to the change in voltage uh, will be different.
Thank you. That answers this question. That's it.
Yeah. So if any no more questions, then I would like to go to one interesting example, that is piezo-resistive based simulation.
Sure, you can go ahead, please.
Yep. Okay. Okay, so since it's a little time consuming, I have already run the simulation, but let me also run it one more time. So this is the potential that we are seeing. So let me close this. Okay, so this is a specific geometry where it has a edge profile at the bottom, and we have the wire connection, the metallization connecting four different piezoresistors. Okay, so this is a piezoresistive based pressure sensor device. Again, the story goes like simulation, material, load, boundary, mesh analysis. So we go to simulation, and yes, we select piezoresistive this time, and we perform stress displacement simulation. And we apply material properties. In the newer version of the software, which we released recently, uh, we define. Earlier, we had this practice of defining pi coefficients alone, pi 11, pi 12, pi 44. Later in 9.1, we introduced something called as concentration. So based on the N type of Si, silicon material, what temperature the doping was being done, and the depth versus concentration file gets used to upload. It's a small text file. Okay. So, and with respect to process now, you can see that we are defining a type of dopant, ion type, boron, phosphorus, arsenic, energy type, what is the dosage, target, and annealing temperature, oxidation process. So this level of data is fed to the software for defining the piezo resistors. So it obviously considers the depth, the concentration, and the resistivity of that material. So we had this question from many of our users that can I change my annealing temperature, because I really don't know how my pi coefficients would change when I change my annealing temperature. So then we have a problem. So instead, so define the physics based on annealing temperature, and then that takes care internally. So we can define this using the process, and we fix the boundary condition. The boundary is check only the boundary is fixed like this. The regions which are shown in red are the ones which are fixed. So with this, let me run the simulation. Simulation would take a minute or two.
So I noticed you have this tetrahedral or irregular meshing. Is there any reason for that? Or can't we use bricks or Manhattan meshing?
Yeah, that's a good question. So this model that we have extracted used from the process simulation. So it was not directly done using using the
Geometry?
geometric approach.
Okay.
Yeah. Yep, my simulation is done. What did we do with the simulation now is we identified the stress displacement with piezo resistive material as such, and then we see due to the we applied a pressure value of 0.1 megapascal, that is 1 bar of pressure on this face, and it is positive, meaning it is from the top to the bottom.
So it is at atmospheric pressure.
Yeah, 1 bar of
1 bar.
pressure.
Yeah.
Yeah. So this is the displacement. Okay. So now due to the displacement, we see, where is that? Mises. The stress profile. Okay, so the stress profile is seen. So now piezoresistive based MEMS pressure sensor has two types of physics now, two types of simulation. One is mechanical based simulation, another is electrical based simulation, because the output that comes out of these resistors will always be a potential. So this piezoresistive pressure sensor works on the principle of Wheatstone network. So Wheatstone network has an option. The way that it is analyzed is at two different points we define the voltage, and another two diagonal points that are left we analyze the output voltage. So here one of the diagonal points we give the input, and another diagonal points we check the output. So and these resistors change with respect to in the case of Wheatstone network, the resistors can be changed due to the change in resistance. There is a change in voltage drop. Whereas in a simulation case, what we have is the change in pi coefficients, or due to the concentration power or the annealing temperature, the resistivity would always be the resistivity may change. In such situations, then the software can take care of such unknown stuff by itself, and then produces these kind of profile. So once the piezo resistors are deformed, when the piezo resistors are deformed, its resistivity will change. Due to the change in resistivity, there is a change in voltage drop. Okay, so the same principle of Wheatstone network is applied here. So we have performed a mechanical simulation. Let's go to electrical simulation. So now the displacement data and the stress profile is recorded at the back end, and only we have these resistors and the wires. So what we do is select the voltage phase, and we apply 5 volts, sorry, 0 volts to this portion. We have to quickly run the simulation again.
We have a question, Dr.
Yes,
Raja. So, like, do we need to do the mechanical simulation first and then using the data later to fit the electrical simulation?
yes. For piezo-resistive type, yes, because based on the pressure that gets applied, the deformation will change. Deformation changes because the stress is different or it is more. So due to that, due to the deformation, the piezo resistors will expand. If the deformation is more, then piezoresistive expansion is much more. That will change the resistivity, due to which change in resistance causes the change in voltage drop. So this catch is what we take, and then we try to extract the pressure values uh, of the applied pressure. So we when it comes to implementation, so we have a pre-calibrated data that this change the change in voltage uh, is seen as an output and is mapped to the pressure value that is seen that is coming through.
The electrical simulation is the second part,
Second part of it.
always,
So now I
always.
extract the electrical mesh, and this is purely electrical simulation. Now at the back end, for this simulation, the stress data is recorded already. So I would apply 5 volts to this, and then I apply 0 volts to this point. So here you may notice there is a small gap between the two. It's not really connected. Okay. So same
Mhm.
is the case of Wheatstone network. Now go to loads. No, sorry, temperature, phase. You need to tell the software that these resistors are at room temperature, or the temperature that you want to define. It need not be 25. Plate mechanical. Sorry, I applied temperature. So now I need to mesh this to 5, 5. The value 5 that I'm applying is the element size that gets created. Plate mechanical mesh. Yeah, so once this is all done, we run the simulation, that is electric based simulation. For the mechanical based output, we run the electrical simulation.
So, there is no way to link the two in the beginning itself so that it automatically moves from the mechanical to the electrical simulation on its own.
No, because the stress profile data is crucial for it to simulate. So the full geometry itself, you cannot link it up in such a way that the electrical simulation is triggered only after mechanical simulation automatically. You cannot do that.
Okay.
So now the potential that is generated. So here we had applied 5 volts, and here we applied 0 volts. And now we will see that what is the voltage node value here. The node value here is about 5 volts. So we will see the node value here. It is 2.50. So 2.50 minus 5, and it is 2. Yeah, so it is 2.5009 kind of a thing. So now what I can do is for the applied pressure, we can change the pressure value and redo the simulation again. If we do that, then we can check the sensitivity of the device.
So we can parameterize the pressure value to
Yes,
go it from a range, let's say,
yes, yes. So I can show you that in another window. I can close this. So let me close this.
So it means we can apply pressure in steps also.
Yes, in the steps you can apply. Yes. Yeah. So you can check that you can apply input value range from pressure to pressure increment.
There is a question, Shripad,
Yes,
from
yes,
Alma. He's asking, will the software determine the change in the resistance or we need to do calculations?
yes. You have to do the calculation. You can get the VI characteristics. Based on that, you can extract the R. So at the end of the simulation, you get the current density, the current that is in the flow, and the potential. So a drop. So based on that, you have to extract your R.
so the software does not plot an R.
No, no.
Okay. But we can get a VI curve.
Yes, you can get a VI curve. Yeah. So this way you can change the, you can always change the values of the applied pressure and do a parametric simulation. Okay, so I've covered the typical multiphysics type of simulations that are uh, touching the thermal, electrical, mechanical, thermo electromechanical coupled such devices. So, do you, any one of you has any questions? You can always raise it now.
We have a question from Almur again.
Yes,
Did we also mesh the resistors during mechanical simulation?
yes, yes. The lines that you see, we did not do it. The geometry already had it, and I have run it as it is. We can always add more mesh to this. The element size can always be reduced. Okay,
So,
so typically, yes,
one more
yes.
question I received on the chat is physics of near field radiative heat transfer with poly, polarizations available? Polarizations?
Let me, what is that? Let me just stop sharing and see the chat box.
Oh no, this one I got it on my on chat. So this person, Swayam Prakash, he is not able to post the question in the chat for some odd reason.
Okay.
Yeah, but I can put the question in the
Sure. Can you
chat.
copy paste that?
Yeah, I did copy that.
Yeah. Okay. Okay. Is physics of
Claritones. Yeah,
near field radiative heat transfer
with
with
polaritons. Yeah.
polaritons available? Well, that's a good question. Uh, Probably I'll discuss this and then come back to you tomorrow on this.
And yeah, that's sounds good and reasonable, Professor Raja. And there's one more question right above that. How can we apply a
Yes.
standard PDK to a designed geometry?
Yeah.
So I
Radiative.
think the PDK discussion, like, will it be part of the
Yes.
training tomorrow?
Yes. Process driven. Yes, it will be a part of tomorrow. Let me also give the perspective of FEM uh, on the node PDK. Okay. So here, in the case of a PDK, um,
We
what we
cannot
do.
see. We cannot see your
Yeah,
screen.
sorry. Yeah, that's right. Okay. So in the case of PDK, uh, if we are using, let's take an example of MEMS cap. So if we are using the MEMS cap or any other PDK, then we are bounded to work in the dimensions that the PDK or the foundry defines with respect to the processes. Okay, so that geometry, if it can be created, that geometry as well can be pushed to FEM simulation. So you can push a geometry that is typically looking like a wet edge profile, but still you can push it for FEM simulation. Okay, the wet edge profile meaning it's a sidewall angle. We also did a simulation a long time ago where the scalloping effects were seen on the accelerometer proof mass. Even that we were able to export it to FEM. So that scalloping effects is really not scalloping, to be honest. It will create a near step profile in the accelerometer for it to mesh and do the adjustments. However, that is very deterministic in terms of the mesh condition that was done for a scallop based DRI profile. So in that way, on similar lines, the PDK can also be derived or designed, and then the MEMS device which adopts the PDK can also be pushed to multiphysics simulation.
More questions right now in the chat.
No questions? More
Yeah,
questions?
no other questions.
No other questions. Okay. So I've talked about the thermal, electrical, mechanical based simulation, and I just give you a glimpse of how to draw the geometry and then export it to multiphysics simulation. So let me show you another approach that is typically recommended for any beginners is through the blueprint module. Blueprint module is a layout editor. Basically, we can create any kind of structures here, and it can always be imported uh, to 3D models. Okay, so here let me take this case of a circle, probably. Yeah, so here Okay, giving you an overview of what blueprint is. Here we define any geometry with multiple layers. We select or define multiple layers. So layer 1, layer 2. We change its color just to ensure that the geometry is not confusing the user. So typically layer 1. So we have in the first time when you try to use the software blueprint, you can see that the command line will never be enabled by itself. You should enable it by check this box. Okay, once this is done, here it is when we click the geometry, you can see that there is a message at the bottom, specify center point for 2p, 3p. So 0, 0. Press enter. That's the center point for a circle. What is the radius? If I write the radius outside the bracket, then it is a radius. If I write within the braces, then it's diameter. So I wouldn't use that. I just say 100. So now the radius is 100. So now if we measure this, it should be 200. So we are there. So dia is 200. Okay. So similarly, we can draw one more geometry. 0, 0. So which one above the other now? So one above the other. And this is the layer order. Layer 1, layer 2. Let me save this file. Just saved it. I have two options now. I can either define the thickness here itself, or I can define the thickness in my blueprint. So as beginner, I would recommend not to hassle with the thickness definition in blueprint. Just save your file, leave the place, and go into 3D Builder module. Automesh, browse, circle. So now the question is which mesh to take. So now it's a circular parameter, circular geometry. Obviously, we cannot take Manhattan. So whether it's isotropic, adaptive. So isotropic is what by default I would recommend. Then click OK. So this creates a tetrahedral structure, which is layer one above the other. I can always check the mesh compatibility. It will show me the current status. So now you may observe that the thickness is by default 1 micrometer. So that can be changed to 10 micrometers. And we don't see a gap. So introduce a gap by adding a new level. Here you can see, click on add a new level. You can see 1. So there is a gap between. So what should be the gap? Select that level and then modify its height. And the next one is modifying its height. So now we have two different geometries which are having a thickness of Sorry, I should have had this gap. So the gap is here. Okay, I think I should delete that layer. Instead, add level. So it should be above level 0, below level 0, sorry. And now, sorry, add level. So above level 0. Yeah, so we have this geometry now. So this becomes a tetrahedral mesh. So if we take the Manhattan mesh, it is generally for cubic structures. So we don't recommend that. So save this file. So where is the starting point? Blueprint, then import it directly here, then push it to analysis. So it's again the same story. Stress displacement for mechanical stuff, thermoelectromechanical for electromechanical stuff, heat transfer, thermostress for stress due to heat. Okay.
We have a
So
question.
yes,
What file types can we upload to Blueprint in the 3D builder? In these levels, is there a way to reorder levels instead of deleting and rebuilding?
yes. There is always a provision to do that.
So, you're speaking about reordering the levels?
Yes.
Okay.
So let me go back to Blueprint, reordering the levels. Okay. Say I would have one more layer that is added here. For whatever reason, I wanted to say, I will say this is layer A, this is layer B, and this is layer C. Okay, so now it's important to have a unique GDS ID. Make sure that it has unique GDS ID or else it won't import into 3D Builder. Okay, so now in the C case, we have A, we have B, we have C. So in the C case, if we draw a rectangular geometry for whatever reason, now then I realize that no, this fellow has to come below. Then just use your mouse, pull him, and then position it. So this is layer reordering it.
That's great. And the other question was what type file types can be
File
uploaded to
types,
Blueprint?
yeah.
Yeah.
So in Blueprint, you can get GDS, DXF by default, CIF, and image file also. But I think most DXF and GDS should do the job for you in Blueprint. We can
And the
export, we can
export is
also
also
import. Yes.
Okay, export is also possible in all these formats.
Yes.
Okay, please continue, Dr. Raj.
Yes. Yeah. So yeah. So we can also export it. Okay. You can also export it to VB script. So now same geometry. Assume that we are working with array-based devices now. Assume that we are working with array-based devices. Then what do I do is these are there are few unions intersection which we'll talk about it tomorrow. What we see here is a matrix array. So typical, how many columns do we want? I would say I require 50 columns and 50 rows, and typical diameter of this is about 200 micrometers. So column spacing can be 250 micrometers, because I would consider from the starting point 200 micrometer covers the dia of the geometry, and another 50 is for the dicing area. Then in the x and y direction I have this set, then click OK. So now I have so many geometries. Matrix. So I have 50 of them. I can import this directly to 3D Builder. 50 is too much, I understand, but what I'm trying to tell you is if there are multiple geometries that goes to a part of system, then you can always simulate it. So you may measure that in this case, the distance between the two files is 50. I had taken the value 250 because the dia is 200 micrometers, and we are planning to have uh, a dicing area, so that which allows 50 micrometers. So what I'm trying to tell you is um, you can define it based on the foundry specifications. And this can be extracted through 3D Builder, and we can do array-based simulation as well. So we have a typical case of a micro mirror where array-based devices is what it works through. So it does not, though we try to optimize one device, we always use multiple devices to work together, because that's how the micro mirror works in real case. Any questions at this point of time? Then,
Nothing in the
yeah,
chat, but I think we
yeah,
can take a final 5 to 10 minute break. There's one question that has come up.
yes.
Do we need to re-upload the 2D to 3D builder when we do any changes in the layout?
Yes, that's a good question. Yes, any changes that you make, you have to put it to a 3D builder and then push it to FEM again.
And I have received some question on the other on my own chat as well.
Yeah.
So one of the first question is it possible to export 3D geometry from SolidWorks into the software?
You can just view it, but importing it is difficult. But let me check with my colleague. So you can import it and see it in a module called Mesh Manipulator, but you cannot convert that to IntelliSuite compatible file.
Okay, and the second question was, can the software simulate optics, laser light, or plasmonic oscillations?
Well, no, we cannot do that because the computational or the numerical methodology for both of the structures is different. In the case of MEMS, we use FEM and BEM. But in the case of optics, we have an issue is it is FTTD or ray optics method. In the case of MEMS, it will typically be in terms of micrometers. So FTTD is applicable. But what I would recommend is if you have a tool like Lumerical, which I had tried this much longer, that we can play with this file STL file. So the STL file from Lumerical can be opened in IntelliSuite, and then from the IntelliSuite deform structure can be opened on Lumerical. So, and that's how we used to play. That's the arrangement that can be done. So since the two numerical uh, computational requirement cannot be fit in one package, we don't have the optical based the light as an input or light as an output related to any simulation optical.
Thank you for answering that in detail, Dr. Raja.
Okay, so here let me okay, so I have given you a glimpse of how to run
Okay,
simulate.
we cannot see your
So see the screen. Yeah, I had stopped it. That's right. Yeah. So we had seen the case of thermal, electrical, mechanical module uh, type of device simulation is what we had seen. And now we shall repeat that with respect to parametric designer. Parametric designer is structural parametric designer. Okay, so I want to do multiple designs because I want to optimize the design, for which I need to do a lot of designs for me to optimize it. So now I don't want to spend time designing with very small increments. So in such cases, you can always use this module called parametric designer. So what you are seeing right now is a case of an accelerometer. I mean, this is just a typical case where it looks like the center part is the plate and the VB script, what we see is the beams that are connected. So something like this. It is something like this. I was just preparing things just during the break. So this is how it looks like. So what are we trying to do? So what we are trying to do is we are trying to define a VB script called G length. Wherever G length is there, from 100 micrometers to 200 micrometers, in the increment of 10, there will be a change in length. Okay, in the increment of 10, and then we perform a natural frequency analysis on this file. So finally what we get will be a natural frequency dimensional change with change in natural frequency. Okay, so this is a one-time activity that we set and control center. So where are these elements? Before going that, we have these elements. So we have two port, just like the piece-wise netlist, you can drag and drop them. Okay, so these are the elements that we have, the MEMS elements, parametric elements. So these are VB script based elements where you define the length, width, the initial length and width. And then in the control center, we start parameterizing the layout. So based on how does this module work? Now I have a base length of the cantilever beam that is suspended to the proof mass is about 100 micrometers. That has to increase it to 200 micrometers in the increment of 10. In such cases, we can create multiple layouts and then we can try to mesh the design and then start meshing the design. Okay, so now I want to apply boundary conditions and loads. So when I click, this geometry opens up, the base model opens up in thermoelectromechanical module. There I set my simulation. I would want to do frequency-based simulation, then apply OK. I want to fix the boundaries. And the load, since this is an accelerometer, I would apply, say, 5G. I save this. Oh, sorry. I think I'm trying to do a natural frequency analysis. For that, we don't apply any load. Okay, so I just saved the file and click OK and then click Start. So apply boundary conditions and loads. Then I go to solver. My computation power can be higher, so I can set this and then a 64-bit is what we take. Save the RTL file, meaning result file at each run. So now what the software does is the accelerometer base design for the length of 100 micrometer to 200 micrometer. There will be an increase in the beam length in all four sides together. And at every 10 increment, it calculates the natural frequency and then finally plots the graph. So we take a 64-bit solver, then we click OK, then we start. So now it has to run natural frequency analysis for 10 different geometries. So this parametric simulation, what you saw is in terms of X and Y changes in dimension. In the case of thickness, it is not a VB script. Instead, it's a global parameter in the parametric, in the thickness parameter itself can be changed, which I'll show you in the next example. Since this is a 10 different step as are to be completed for simulation here, maybe it would take about 2 or 3 minutes, or probably typically 5 minutes or so. So what you're seeing now is it is creating RTL file. RTL file is the result file. So now the second geometry started running. So you can see the progress of the simulation. Meanwhile, anyone has any questions?
In the chat so far.
Okay.
So Sripat, I have a question on this
Yes.
accelerometers. So that's a simple structure. How
Yes.
about with structures with springs, serpentine springs, and
Yes.
complicated structures? Or
Yes.
so how we can
Yeah.
parameterize that?
Yes.
Or
So
or
you
we will
can
be just a
parameterize.
component.
Yeah. So if it is thickness parametric simulation, it's a straightforward UI based. If it's a X and Y geometry, that is horizontal or the planar geometry parametric, then VB script, a small VB script needs to be written. That is one option. Another
So
option is,
sorry, just to for the clarification. So we can make our own macros in
yeah,
VB script. Okay,
yes, you can do that.
okay. Please continue.
That is one. Another option is we have accelerometer gets created using a layout tool, and we can link the layout tool to parametric simulation to parameterize the geometry.
Okay. So would it be possible in next couple of days if you can show us any simple example, like just make a cantilever beam and link it to the
You mean through
parameterized
the
geometry?
layout file?
Yes, an
Yeah, I think
example, a
I'll make a note
demo
of it.
example.
I will create one case and then show it to you tomorrow.
Okay, thank you.
Yeah.
There is a question also Suraj has put in the chat.
Yeah.
So have you asked that question or this needs
Uh,
to be answered?
what is the question?
Is it possible to export 3D geometry from SolidWorks into the software?
Well, I have already answered that.
Okay.
You can just see it, you cannot convert it. Yeah. Second one also have been answered.
Okay.
Yeah. have one more question uh, from Almur, and can we parameterize length and width in a single simulation, or we have to do each parameter at a time? Dr. Raja?
Oh, sorry, I didn't realize I was on mute. Okay, so here, okay, so here the answer to this is consider to parameterize one parameter at a time, because if you start changing two parameters at a time, you don't know the result is specific to the change in parameter one or parameter two. So it's always better to change one at a time.
Yeah, that sounds like a reasonable approach. Yeah.
Yeah. So we are almost there, I guess. I think couple of more geometry uh, with completion of simulation. So here as well, I was just also referring this. Let me also show you in the interest of time. Here you can the base can also change the input load as well. So define the parametric load. So when we go to uh, TEM for applying boundary conditions and the loads, you can also change this and then you can run the simulation. So here in this case, what you see is the change in accelerometer from range 1 from point 1 to point 2, and for which the displacement is seen. Okay, so maximum Z displacement with parametric load, that is pressure. Okay, so in this case is what we see. Um, Yeah. Okay. So we have one more case in the document. It's in the tutorial, is the comb drive structure in parametric simulation. So we have the typical code. The VB script is written, and these VB script should be able to help any beginner to start using the tool. So same thing gets extended to piezoelectric as well. So you can do parametric, structural parametric simulation using piezo for piezoelectric based devices also. So you can parameterize input variables. You can parameterize the structural. Yeah, it's done. So let me go to results. So you can see the frequency values change, for mode 1, 2, and 3. So parameter value is 100 micrometer on the x-axis, 100 micrometer to 200 micrometer. On the y-axis, the frequency change. So with the increase in length, so it's obvious that frequency reduces, but the amplitude increases. So that is seen in this graph. So you can parameterize based on accelerometer, acceleration input. You can parameterize based on one parameter, that is with respect to length, width, and thickness. Okay. So this is something that will really help any MEMS designer, because most of our time goes changing, making incremental changes to the geometry. So similarly, we have multiple. Just to get familiar, so we have various examples in this module, so you can get familiar with many. Okay, so this is about the parametric simulation. So you can also push this to Excel file for plotting the way you wish to. Okay. So this is the model that gets created. Okay, so any questions at this point?
None in the chat so far.
Okay,
I'll let you know if something pops in.
okay, sure, thanks. Okay, so here is a file. So here, these are file elements. Element property. So what is this? This is a layout. This is the layout file. Kader, probably I think I'll run this example just to show you how so this is a this is a two-layer geometry, a piezoelectric beam simulation. Okay, so here this is the layout that I'm trying to link to a parametric designer module. Okay, so this is the file. Okay, and for which I go to global parameters. Sorry, I think for this we have layer manager. So here we, okay, so for X and Y, it is VB script. In terms of thickness, it's the UI. So here you can see that from 4 to 10. Okay, so silicon. So we leave anchor dimple structural. So here we take piece 80 as my first layer, which is below, and then from 4 micrometer to 10 micrometer in the increment of 1. Okay.
Okay.
So now, sorry. Yeah, I think I'm a little messing out. Yeah. So that's right. So 4 in terms of 1. So now once it is done, the thickness is done. The global control center, I start. So this has produced multiple layers of geometry in that increment, and then I mesh the design. So this is the starting design. So let me refer to this document. It's been quite a while now. Yep. Yeah, so probably missing the flow. I need to refer the document and then redo it. Probably, I think I would still do with the flow. Uh, Probably tomorrow, I guess, Kader, because I have to read and do it. This is not the place to do all of these things for me. It's been quite a while that I've done this example. So in one go, I would still do it tomorrow.
Okay, no problem.
Yeah.
Thanks for this demo.
Yeah, but anyways, so the overall thing is here you can see that yes, so you with change in thickness, how the other parameter like the displacement or the potential can change is what we can also look at.
Okay, that's great.
Yeah, so I'd like to take a pause for this example here itself. Let me not continue this. Tomorrow I'll do that. So yeah, I think whatever I plan to do it for today, I think I'm done, except this the workflow that came up now. Uh, Let me try to summarize what I've done till now. It's about creating 3D geometry using 3D Builder module and exporting that to thermoelectromechanical based on the type of analysis that you want to do at a static, frequency, and dynamic. Uh, we performed a few simulations, and specific to the physics of the problem, we also checked how the physics of the problem can be defined based on thermal, electrical, mechanical. It's a coupled device, coupled physics problem. So based on that, we were able to see how to apply voltage and see the deformation, apply pressure, see the deformation, apply range of voltage to plot the graph. Uh, then we moved to the advantages of using a 2D layout and then pushing it to 3D and then pushing it to multiphysics simulation. And we have seen how piezo-resistive based simulations, which is a combination of mechanical and further connecting the electrical simulation, how it relates to each other as what we have seen. And moving ahead of that, once those basic simulations are quite understandable, then if we are at a stage to optimize the design, for which we spend a lot of time on incrementing or making small increments to the designs, for which we recommend the users to use parametric designer module. So in parametric designer module, we have three ways of defining the geometry. A is through the VB script, B is through a combination of VB script and elements, and the three is the linking the layout with its with the VB with a file. But the linking the layout, the simulation uh, will be continued tomorrow. But however, the overall point of using the overall point of using the parametric designer is to inform you, or to tell you or to teach you that this module can save a lot of time for you. Okay, so you can parameterize input variables, you can parameterize structural as well. Okay, so that's the whole point of today's session. So I'm here for another 20 minutes. In case if you have any questions, probably I would take it up.
So much, Dr. Raja, for an insightful training and session today. So we do have a question from Elmore. The best approach you suggest is to follow blueprint plus parametric designer plus 3D builder. Is that correct?
If you are in the stage of optimizing the design, then this approach is good. But if you are still not figured out the simulation settings that are required for the device that you are trying to do, then don't get into parametric simulation now. Do the simulation settings for for an individual device and set the simulation, and better get confidence with the simulation settings that you are trying to do, and then get convinced that what you are getting output in such simulations are quite logical. Only then you jump into jump into parametric designer. uh, Else it would really create a chaos for you, because too many variables start playing roles.
Also saves you going through a lot of computation time so that
Yes,
you might have more accurate results with your parametric simulation.
yes, yes. So it all depends on what stage are you in. Are you a beginner trying to set the simulation itself?
I think in that case, we can end the training session for day one. Thank you everyone for joining us, and special thanks to Dr. Raja for joining us all the way from India and giving a detailed overview of IntelliSuite capabilities and providing a lot of insight into how multi-physics simulations can be done using the tool. I encourage every one of you to participate in the training session tomorrow, and the time remains the same, 12 p.m. to 4 p.m. Eastern time. But today, we jump into a lot of interesting capabilities of that are very unique to IntelliSuite, where microfabrication simulation module can be used to actually visualize and simulate your designs as per the fabrication parameters. So looking forward to tomorrow's session, Dr. Raja. Thank you so much for giving your time today.
Yeah,
And
thank
thank
you
you
very
everyone for
much.
participating.
Thanks, Kader, Suraj, for facilitating this. So tomorrow, all of you, we will see you tomorrow. Pull in your fab friends at Foundry engineers who are struggling to optimize the processes to get them attend the session, because what we see tomorrow is something unique, novel in IntelliSuite software. Okay. Okay.
Thank you,
Have a
Okay.
good
everyone.
day.
Have
Thank
a
you.
great day.
Bye bye.
Thank you. Bye.